This is joint work with Chen, my advisor, Andreas Haeberlen, Wenchao Zhou, and Boon Thau. So this talk, as Mila mentioned, is about fixing bugs in networks. To make things more concrete, let me start with an example. So suppose we have an SDN network that connects the internet to two servers. So the operator programs S0 in the middle to forward all requests to S1, and told S1 to forward this request to the main web server. So however, at some point, the main web server becomes overloaded. So now the operator provisions another web server. Right? They reprogram S0 to load balance between these two web servers. And now, the operators must forward this offloaded request to the backup web server. They observe that the logic here is very similar to what was written for S1, right? So they just copy and paste the code, the line 3, from line 2 to line 3. They did adapt the output port number, right, from 3 to 4. However, they forgot to change the switch ID. Right? It's still S1. So as a result, instead of forwarding packets, S2 actually drops all of these HTTP packets. So now the operator has the problem, right? So why is the backup web server not receiving any requests? So how to solve this problem? Right? How the operators keep their job? So first, they must diagnose the problem. So this can be very challenging, but there are a lot of tools such as NetSite and Why Not, which can help you. Right? So however, diagnosis is just the first step. So the operators, they still need to find an effective fix. So existing tools actually offer a lot less help with this second step. So let us see what existing debuggers will do in our network. Okay. I will shamelessly use our own debugger, Why Not, as an example. Right? Going back to our SDN network, so the web server is not receiving any requests. Why? So Why Not can explain this. So the server did not receive such a request, right? Because although they're coming in from the internet, right, there was not a proper flow entry on S2 that could forward these requests. This helps a lot with diagnosis, right? Because now you have a causal explanation of the symptom. So can we use existing tools such as Why Not to find repairs? No, we cannot, right? Because we do not know which parts of the program should we change. Right? It is hard because there can be many possible ways to change a buggy program. And if you randomly enumerate all of these changes, I can guarantee that the majority of them is not going to fix your problem. And while the remaining few may fix the problem at hand, right, it might cause the HTTP server to receive requests, they may cause side effects in your network. So instead of trying all these possible changes, what you really want are targeted repairs. Right? A small number of repairs that precisely fix the problem. So this is the goal of our work. So our approach is to use a concept called Prominence from the database community. It is useful for diagnosis because it can explain how an output was computed. So it usually looks like a tree. Right? The output at the top is caused by inputs at the bottom. So however, Prominence cannot help with repair, right? Because you still do not know which parts of the program needs to be changed. So in fact, if you look at the tree that I just showed for Why Not, the program is not even in the Prominence. So our work extends Prominence to meta-provenance. So it does not only tell you which inputs contributed to the output, but also which parts of the program contributed to the output. So this new data structure can help you with finding repairs, right? Because it will tell you where in the program can you make effective changes. So here's the overview of our approach. To fix the problem in your network, we use Metaprovenance to build a repair button. So it takes as input the symptom described by the operator. There are 3 steps. First, we build the Metaprovenance data structure. This will tell us what should be changed in the program. Next, we found what value we should change to. This will give us a list of concrete repairs where each one of them is designed to fix the problem. And last, we will backtest these repairs to avoid side effects. The result is a couple of targeted repairs that precisely fix the problem. So next, more about these 3 steps. So first, given the symptom provided by the operator, how do we build the Metaprovenance data structure? So let me give some background first on provenance. Right? You can explain how outputs are computed from inputs. So consider Bob. Right? Bob has to present the paper at NSDI. Right? So how did Bob arrive at NSDI? Well, his flight departed from gate 9, and when the flight departed, Bob was at gate 9. So why was Bob at gate 9? Because he arrived at the airport, and his ticket said he should go to gate 9. So notice that in this provenance tree, vertices represents events, and edges represents causal relationships. So provenance works well for Bob. We can apply the same approach to networks. So this is the provenance of HTTP request. As you can see, it only includes those inputs that actually matters. Suppose you have 1 million packets in your network. It's only going to include those packets, those few packets that actually are causally related to this web request. So however, provenance only explains things in terms of inputs, such as packets and flow entries. We still do not see the program in this provenance. So what can we do about it? So we need to capture how the program works. So we use a simple specification called a Metamodel. So it is in the paper. Please do not read it. So this model basically teaches the algorithm what a programming language does. So writing such a model is a one-time effort for each programming language. So we'll apply provenance at this meta level. For example, right? So why is there a HTTP request? Because there is a matching flow entry. So why is there a matching flow entry? Because an if clause in your controller program was executed. Right? Why was the if clause executed? Because there is an equality condition in your if clause, and the variable on the left and the constant on the right has the same value. As you can see here, the resulting provenance not only tells you which inputs contributed to the output, but also tells you which parts of the program contributed to your output. And sometimes the symptom can be that something failed to happen, right? So how to generate provenance in this case? So the basic technique we use here is called counterfactual reasoning. So here is how it works. So suppose Bob, right, did not show up at NSDI. Right? So why did he not show up? Well, his flight did departed from gate 9. However, when the flight departed, Bob was not at the gate. So why was Bob not at the gate? Well, he did arrive at the airport. However, his ticket did not say gate 9. It said something else. So Bob went to the wrong gate. So this is the gist of counterfactual reasoning. So we can apply such reasoning to meta-provenance. So it will look like this in our SDN example. Right. So why is there not a HTTP request at the backup web server? Because there was no matching flow entry. Why was there no matching flow entry? One reason is that one if clause in the controller program was never executed. So why was it never executed? There is an equality check in the program. During the execution, the variable was S2. However, the constant was not S2, it's S1. So this is a key benefit of meta-provenance. So while this program can be very large, it can have hundreds of lines, so meta-provenance will find parts of the program that can be changed to affect the symptom. Right? For example, it will tell us you should consider changing this constant. It will also tell us there's no need to change the action, right? Because it's not even in the provenance. So once we know what should be changed, but what concrete values should we change to? Right? This is what step 2 is for. So given a provenance, we can change the leaves in the tree to affect the root. For example, suppose Bob's ticket was cracked, he would have shown up at NSDI. But what concrete values should we change the leaves to? So the idea is to collect a set of constraints on what the change should look like. So here is how it works. So in order for Bob to arrive at NSDI, so Bob must show up at where the flight departed. So now we have a equality constraint. Bob will also only show up at the gate which was printed on his ticket. So this is the second constraint. We can solve these two very simple constraints and extract a repair that says, you know what, the ticket of Bob was misprinted. It should have said gate 9. So the constraints here are very simple, just two simple constraints. In practice, the constraint pool can be large and complicated. Therefore, we have using solvers like Z3 to find suitable values. So for instance, we can apply the same idea to the network, right? So why is the web server not getting any requests? So we can extract, given this meta-provenance tree, we can extract a concrete repair. We're going to change the switch ID from S1 to S2. This will precisely fix the symptom because it will cause S2 to forward this request to the backup web server. Right? Again, this is the key benefit of using meta-provenance. It can generate targeted repairs. So all these repairs, they are specifically designed to fix the problem, but not all of them are equally good. So some of them are really complicated and are probably not the ones that the operators really want. So soft engineering studies have repeatedly shown that simple repairs are more likely in practice. So therefore, we rank repairs by their complexity. For instance, if you only change a constant, the repair will have a low cost. If you completely rewrite the if clause, the repair will have a high cost. We'll explore repairs with a low cost first. So the first two steps gives us a list of concrete repairs. However, some of them might cause side effects. To make things more concrete, here is an example. So the problem is that the backup web server is not receiving any requests. So one repair is to completely delete this if condition. So now the controller will send a copy of each packet to port 4. So this will fix the problem, right? Because S2 will send all requests to the backup web server, which is at port 4. However, this will cause a side effect. Right? S1 will now also send all the HTTP requests to the DNS server, which happens to be at port 4. Right? This is not good. What can we do about it? So the idea is to backtest these repairs using historical data. I'm not going into details due to time limit, but basically we're going to collect some data at runtime and replay the repairs against this data. And we'll prioritize those repairs that do not cause significant disruptions to the distribution of traffic in your network. So backtesting multiple repairs one by one can be very slow. Unfortunately, we can use a technique called multi-query optimization to backtest multiple repairs in parallel. You can find more details in the paper. So now that I have told you how it works, let us see how well it works. So we have implemented a prototype that supports subsets of 3 different SDN languages. One of them is declarative, and the remaining 2 are imperative. So we want to be realistic, so we took 5 bugs from previous papers and reproduced them with real topology and real traffic. And by the way, the prototype can extract provenance from these programs automatically. We evaluate the prototype to answer these 5 questions. Due to time constraints, I will only cover 2 of them today: the quality of repairs, as well as how long it took to generate them. You can find the rest in the paper. So how is the quality of repairs? So in our example scenario with the copy and paste error, we generated a total of 9 candidate repairs. So each one of them will precisely fix the symptom. It will cause the HTTP server to receive some traffic. So 7 of them are too aggressive and did not pass backtesting. The remaining 2 are working repairs, and the second one here, changed the switch ID from 2 to 3, is probably the one that the operator would have intuitively chosen. So this is consistently true for all the other scenarios that we tried. So in all scenarios, the number of repairs we generated is consistently less than 15. So you might be curious, what does this mean? But notice that some previous solutions basically use a shotgun approach, which tries a large number of repairs. So unlike them, Metamodel generated a small number of targeted repairs that precisely fix the problem. And by the way, the backtesting further reduces the number of repairs. So before I conclude, how long it took to generate repairs? So in all our scenarios, it took less than 30 seconds. This seems fast enough for interactive use. To summarize, our goal is an automatic repair button for networks, for SDNs. So our approach is to use a concept called meta-provenance, which extends provenance to cover programs. It can find program changes that actually matters, and therefore we can generate targeted repairs. So we evaluated the prototype with 3 different SDN languages. The repairs are effective and can be found quickly. Thank you, and I would be happy to take any questions.
Hi, I'm Jessie Chen from MIT. I probably missed the part. How did you define that the program has a bug? Do you use input-output pairs to see if it's correct or not, or does the person just say that there's a problem?
So the question is, how do we define a bug?
Right. How do you know that there is a bug, and how do you know that this fix is correct?
Okay. So we rely on the only input that our repair button accepts is a description of the symptom from the operator. So that's the only input we need from the operator.
What's
so basically,
the symptom?
For instance, in our example, the symptom would basically say the web server is not receiving any requests.
Okay, I see.
So we don't have a definition for bugs. We rely on the operator.
Okay.
Thank you.
Hi, Sanjay from Purdue. So I've seen that in the programming language community, they have some concept called backward slicing, where they look at the portion of the code that affects a given line of code.
Right.
I'm wondering if you can comment on whether Provenance is similar to backward slicing, or what's the difference?
Yeah. Actually, we discussed the literature on slicing in our related work. I think basically what slicing does is that it reduces the program to a subprogram, which is basically the execution path of the output. So in our case, I think, so first and foremost, that slices cannot generate repairs. Right? And another qualitative difference is that slices is mostly for an output that existed, whereas in our work, we can also support something that did not happen.
I see. And one other quick question is, what aspect of this work is networking specific? It seems like this is very generally applicable. So where are you exploiting something specific to networks? Or?
Yeah. Okay. So the question is, which part of the work is specific to networks?
Yeah.
So first, I think this approach is not fundamentally limited to networks, right? But I think what actually helps us is that in networks, the controller program, for instance, you have these domain-specific languages, right? And the semantics of these languages are simpler than general-purpose languages, such as Java or C++. For instance, in networks, they usually, if you have a network policy, usually the policies for different portions of the traffic are separated. And that can help us, for instance, make the scale like trackable.
I see. Thank you.
Thank you.
Peter Matsko from NetApp. Just being curious, how big are the provenance graphs that you're analyzing, like in terms of vertices, edges?
I think it's in the order of, first it would depend on the scale of your network, as well as like how many lines in your program, right? But I think in the things we have tried, it's in the order of thousands.
Okay. Thank you.
Hello, I'm Andreas Wang from Temple University. Quick question. So when you have multiple target repairs, you're using historical data to backtest to find a correct one, right? So I'm wondering, is there a guarantee that you are able to always find a correct repair? Is it possible that you still, say, end up with a repair that actually has some undesirable side effect? If there's no guarantee, like how effective is backtesting with historical data?
Okay, so the question is, will backtesting miss some like buggy repairs?
Yes.
I think the answer is yes. So backtesting is heuristic. There's no guarantee that backtesting can always find, can guarantee that every single repair is sort of valid. For instance, you might have a very subtle repair, for instance, to cause some small amount of traffic to your secure server, right? But I think, so backtesting, we only use a very simple technique to do backtesting, right? And you can have complementary things, for instance, verification that we have talked about in this talk to further to provide stronger guarantees. Yeah.
Okay, so like in practice, do you have any experience like how likely backtesting can figure out those correct ones from those actually maybe false repairs?
So in our example,
like
backtesting.
How often?
Yeah, in our example, backtesting works pretty well.
Okay, great, thank you.
Thank you.